All right, so let's go through some of your problems for 6.3, working on implicit differentiation. So the main thing that you need to notice that's different about implicit differentiation is that now we have equations where you have both x and y involved in the same side of the expression, whereas before we were only looking at functions where the expression was a function of x. Now we have equations. These are no longer functions because they won't meet the one-to-one requirement, passing the vertical line test in case we need to graph these. But the main thing that makes it obvious that implicit differentiation will be involved is that you have x and y both together in one side of the equation, and it's not an equation that can easily be solved to get y or to get x by itself. If it was easy to get y or x by itself, then we could just use normal differentiation after we got one of the variables by itself, but it would be complicated in both cases to try to just solve for y or to only solve for x. So now we'll solve these equations, or we'll differentiate these equations using the normal derivative rules, but there is one major difference, and that is every time we have to take the derivative of a function expressed as y or a variable that is not our normal variable that we would take the derivative of, which is x, then we just have to apply the chain rule and we'll write dy dx after it. So I'll go through example 1 to show you what it is that I'm talking about. So we normally take the derivative of this as we normally would. This would be 4x here plus, and now we have both x and y, so we have two separate variables, two separate functions, so we'll use the product rule here. So we'll have 4y, if we take the derivative of 4x, that's just 4, and then it'll be plus 4x, and the derivative of y will be 1, but then we also attach dy dx after it using the chain rule. So the derivative of y was 1, and then after you take a derivative using a y variable, you put dy dx after it. So then that would be plus, and we take the derivative here using the chain rule again, we get 8y, and now it's to the first power, but we still put dy dx after that, and then plus 19, the derivative of y is just 1, so then we have dy dx afterwards. And then finally, the derivative of 8 is just 0, so this equals 0 now. The derivative of 0 on the right-hand side of the equation is 0. So now we're trying to get dy dx by itself, so we move away everything in the equation that doesn't have a dy or a dx attached to it. So we move away, we subtract 4x and 4y to the other side of the equation. So we bring everything else down. This will be 4x dy dx plus 8y dy dx plus 19 dy dx equals, and we're subtracting all of this over to the other side, so 4x minus 4y. And now we want to get the dy dx by itself, so we'll factor it out of the expression. So we'll have dy dx, and then we pull it out, so we have 4x plus 8y plus 19 equals negative 4x minus 4y, and then we'll divide both sides by 4x plus 8y plus 19 to move it away from the dy dx, and it will end up over here. So I'll do that on this side to show you what the final answer will look like. So now it'll be dy dx equals negative 4x minus 4y all over 4x plus 8y plus 19. And that is dy dx. Moving on to number 2. We have 7x cubed equals 2y squared minus 3y. So on the left side, we'll have 21x squared equals 4y dy dx minus 3. dy dx. Then we need to factor out the dy dx to get it by itself. So we'll have 21x squared equals dy dx times 4y minus 3. And we'll divide both sides by 4y minus 3 to get dy dx by itself. So it will be 21x squared over 4y minus 3 equals dy over dx. And here is our derivative. Moving on to number 3 now. So number 3, now we have a quotient rule that's involved over here on the right side, but everything else still works the same as it normally would. So we'll have 6y dy dx equals, and we'll do low d high minus high d low all over low squared 4x plus 5 squared. And then we can simplify our numerator. So that will be, equals 16x plus 20 minus 16x plus 20 minus 4x times 4 will be minus 16x minus negative 5 and positive 5 times 4 is 20 all over 4x plus 5 squared. And then we can divide both sides by 6y. So I'll just bring it down here on the right hand side. And we'll have dy dx equals all of this, but the 16x's cancel in the numerator. The 20 just becomes 40. So that will equal 40 over 6y 4x plus 5 squared. And if you want to reduce it further, you can divide everything by 2. So this would be 20 over 3. So that would be 20 over 3y times 4x plus 5 squared. Moving on to number 4. So now we have radical expressions, so we'll go ahead and write those as rational expressions. So I'll change that to 6x to the 1/2 plus 6y to the 1/2 equals 7y. So that will become 3x to the negative 1/2 plus 3y to the negative 1/2 equals 7 dy dx, and we need a dy dx over here behind this y because we took a derivative of a y variable. Now we want the dy dx by itself, so first we subtract the expressions that don't have dy dx. So we'll have 3y to the negative 1/2 equals 3x to the negative 1/2, or this will be negative, sorry, negative 3x to the negative 1/2 plus 7 dy dx. And now we move the dy dx to the left hand side. And I realized I should have just moved the 3y over here instead of making it a little bit more complicated. So let's go back and fix that. So we'll just move the 3y to the negative 1/2 to the right hand side. So going over now, we'll have 3x to the negative 1/2 equals 7 dy dx minus 3y to the negative 1/2 dy dx. And now we factor out dy dx. So that'd be 7 minus 3y to the negative 1/2. equals 3x to the negative 1/2. And then we will divide both sides to get dy dx by itself. So we'll be left with 3x to the negative 1/2 all over 7 minus 3y to the negative 1/2 equals dy dx. Now, number 5, we have an exponential function, but everything else still works the same. So the derivative of e to the x squared y is going to be e to the x squared y, and then we take the derivative of our exponent, so times 2xy plus x squared dy dx. We're using a product rule here because we have a product of x squared and y. So, and then we move on to the right side of the equation now. So that would be equals 6 plus 5 dy dx. And the 8 just goes away and becomes 0. So now we want to get this dy dx over here on the other side of the equation. But in order to get it out of this parentheses expression, we have to distribute in the e to the x squared y to both of these to get rid of the parentheses. So we'll have 2xy e to the x squared y plus x squared e to the x squared y dy dx. And that equals 6 plus 5 dy dx. Now we can subtract this expression over to that side, and we'll move the 6 over to the other side of the equation. So we'll have 2xy e to the x squared y minus 6 equals 5 dy dx minus this expression that we're moving over. So x squared e to the x squared y dy dx. And now all we need to do is factor out the dy dx and divide both sides by 5 minus x squared e to the x squared y. So I'll go to my last step. We'll have 2xy e to the x squared y minus 6 all over 5 minus x squared e to the x squared y equals dy dx. Number 6, you have 4x plus ln y equals x to the 4th power, y to the 6th. So we'll have 4 plus 1 over y dy dx equals, and we're using a product rule here now, so this will be 4x cubed y to the 6th power plus 6x to the 4th power y to the 5th power dy dx. And then we need to get our dy dx's together, so we'll swap these two. So we'll have 4 minus 4x cubed y to the 6th equals 6x to the 4th power y to the 5th power dy dx minus 1 over y dy over dx. Then we need to factor and divide this expression away. So our final answer will be 4 minus 4x cubed y to the 6th minus over 6x to the 4th y to the 5th minus, and we can put 1 over y, but I'll just put y to the negative first power to simplify it. And all of this equals dy over dx. Number 7 wants us to find the equation of the tangent line now. So now we're not only finding our derivative, but we're also going to find an equation of the tangent line. Remember, the equation of the tangent line, you can always write it in slope-intercept form. So you'll have y equals mx plus b. Well, so now we know we need to find the slope as well as our y-intercept. And we're already given a point as x1 and y1 that we can plug into the equation later when we need to. So first, let's find the derivative. Let's find what dy dx is. So the derivative here will be 2x y squared plus 2x squared y dy dx equals 0. And we want to get dy dx by itself because dy dx is going to be equal to the slope of our tangent line. So I'll write that over here just as a note. Dy dx equals the slope of the tangent line. So finish solving over here to get our slope. We're going to subtract 2xy squared to the other side. So we'll have 2x squared y dy dx equals negative 2xy squared. Then we can divide both sides. So we'll have dy dx equals negative 2xy squared over 2x squared y. And this will reduce and become negative. This x will cancel. This squared and this y will cancel. So we'll have negative y over x. So this equals the slope of our tangent line. This is dy dx, and that is the slope of our tangent line. So now to get our actual slope, we go back to the x and the y coordinates that were given to find what the slope is at this point. So we plug in x, we plug in y, that will give us the slope of the tangent line. So that will equal negative, and we plug in negative 6 for y, and we plug in negative 1 for x. So the slope of our tangent line is going to be negative 6. So now I'll write in another color so it doesn't get to be too confusing. So that is the work to find the slope of our tangent line. So now y equals mx plus b, we want to find the y-intercept. So y is negative 6 equals the slope, which is negative 6, times x, which is negative 1, plus b. So that means negative 6 equals 6 plus b. So if you subtract 6 from both sides, b is going to be negative 12. So then our equation for our tangent line at this given point, we plug in our slope into our equation, we plug b into our equation, we'll get y equals negative 6x minus 12. So by now, the work is getting kind of tedious, and you're saying, well, we're doing the same thing over and over. We got it. Is there some kind of shortcut? Yes, there is a little bit of a shortcut, but it's only in the problems like with number 7, where the x and the y are given, and you're looking for the equation of the tangent line. So the previous problems, you were just looking for dy dx, so you did have to go through all of those steps to get dy dx isolated. But now I'll show you one for problem 7, 8, and 9 at least, where you can kind of skip a little bit of some of the tedious work. So again, it only works when you're given a point and you're looking for the equation of your tangent line. So we still start out like we normally do, where we need to find the derivative. So we'll go ahead and we'll make this 4y dy dx minus 1/2 x to the negative 1/2 power equals 0. And now the difference is when we want to get dy dx isolated, we first plug in the known variables, we substitute the x and y into our equation to make it a little bit easier. Because it's much easier to move numbers around the expression rather than moving a whole bunch of different variables. So we'll have 4 times 4 dy dx minus 1/2 16 to the negative 1/2 power equals 0. So this will be 16 dy dx minus 16 to the negative 1/2 power is 1/4. So that's minus 1/8 equals 0. So we'll move the 1/8 to the other side. So we'll have 16 dy dx equals 1/8. And then we'll divide everything by 16. So we'll get, if we divide it all by 16, I'll move it over up here. We divide everything by 16. We get dy dx equals 1/8 times 16. Let's see. 16 times 8 will be 48. 8 times 1 is 8. Plus 4 will be 12. So that will be 128. 1/128, that is, sorry. So now we have dy dx, and we've already evaluated it to get what our slope is. So now, this is the slope of our tangent line, this is our x, and this is our y. So now we just need to figure out what the y-intercept is. So we're going to have, if y equals mx plus b, then y is 4. Our slope is 1/128 times x, which is 16, plus b. So we'll have 4 equals 16/128 would be 1/8 plus b. And then we subtract 1/8 from both sides. 4 is 32/8. So 32 minus 1 will be 31/8 equals b. So now we have b. We have our x and we have our slope, which is m. So we plug that into our equation. So now y equals m 1/128 x plus 31/8, which is b. So here is our final answer. So here I started number 9, which is going to work just like 7 and 8. The only difference is, instead of them giving you both the x and the y coordinate, they only give you x equals 5. So you can use that information to plug it into the original equation and then just solve for the y coordinate. So when you plug in 5 for x and you solve it, you end up getting y equals 3. So now we have our x and our y coordinate, and everything else from here is the same as number 8. Remember, once you get to that initial stage when you have dy, dx all over the place with variables, just go ahead and plug in 5 and 3 to make it a little bit easier when you need to simplify and solve for dy, dx. So now moving on to number 10, it says the equation that's given produces a figure known as the limit set of Bernoulli. Find the equation of the tangent line at the point 3 and 1. So here our point at 3 and 1 is shown on the graph. So we know our slope for our tangent line should be, it should at least be negative and not too steep and not too flat. So we know we're looking for a negative slope here. So now we're going to go ahead and find our derivative first. So we'll have 4, and it'll be x squared plus y squared, and then times the derivative of the inside, so 2x plus 2y dy dx equals 25, and we do the derivative of x squared minus y squared, so that will be 2x minus 2y dy dx. Then again, remember, now we could distribute and FOIL and move everything around to get dy dx by itself later, but what we want to do now is just go ahead and plug in 3 and 1 to make the rest of our solving and simplifying easier. So we'll plug in 3 for x, we'll plug in 1 for y. So we have 4 times 3 squared plus 1 squared times 2 times 3 plus 2 times 1 dy dx equals 25 times 2 times 3 minus 2 times 1 dy dx. Now we simplify. So 4 times 9 plus 1 will be 4 times 10. So this will be 40. And this will be 6 plus 2 dy dx. And that will equal, we have 6 minus 2 dy dx. So this will be 25 times 6 will be 150. 25 times 2 will be 50 dy dx. And on this side, 40 times 6 will be 240 plus 40 times 2, that will be 80 dy dx equals 150 minus 50 dy dx. And now we need to get our dy dx's together. So we'll add 50 over to the left side and we'll subtract 240 over to the right side. So we'll have 130 dy dx equals negative 90. And we'll divide both sides by 130. We'll get dy over dx equals negative 9 over 13. So this is the slope of our tangent line. So now we have the slope, we have x, and we have y. Now all we need to figure out is b, so we can write it into our equation. So y equals m x, and x is 3 plus b. So we have 1 equals 9 times 3 will be negative 27 over 13 plus b. So we add 27 over 13 to both sides. 27 over 13 plus 1 will give us b equals 40 over 13. So now we have our equation is going to be y equals, our m is still negative 9 over 13, x plus 40 over 13. There you go. And just to show you, that this did save us a little bit of time and effort. If we wanted to get the dy dx by itself first, here is what the work would have looked like if we had done that. So we still found the derivative in this first step, but rather than plugging in x and y here, we continue to work it out, simplify it, and then we had to get the dy dx by itself, which we did down here, and then we still have to plug in 3 and 1 for x and y anyway, and we still end up with the same slope. So that's just two different ways of solving it. Again, I highly recommend that if you know what x and y is, once you take the derivative, just go ahead and plug it in and then solve for dy dx afterwards, so you're not using as many variables and variable expressions. All right, so now it says the graph of x squared plus y squared equals 625 is a circle. The center is at the origin. The radius is 25. And it says write the equation of the tangent lines at the points where x equals 20. So notice that it says the points with an s, so it's going to be more than one point where x is 20. So still, they only give us x. We need to solve for y. If you plug in 20 for x, then you have 20 squared plus y squared equals 625. So 400 plus y squared equals 625. So y squared equals 225. So y equals plus or minus 15. So that means when x is 20, we get 2 points. One of them is at 20 and 15. The other is at 20 and negative 15. And if we're talking about a circle that we're going to eventually have to graph, we know that the radius is 25. So here's 25 all around, 25 up, negative 25, negative 25. So here's what our circle roughly looks like. And if the points is at 20 and 15, so here will be 20 and positive 15, here's 20 and negative 15. Here are our 2 points. So we should get a slope that is negative, and we should get a slope that is positive. Also, because it's in Math Excel, it's going to give you an option. You know that your circles with your tangent lines on it should look like this. They should pass through 20 and positive and negative 15. So now, going back to finding the equation now. We need to take the derivative of the original equation, which is going to be 2x plus 2y dy dx equals 0. The derivative of your constant is still 0. And then, so now we can either plug in 20 and negative 15 into both of these steps, but this problem is simple enough where it's not absolutely necessary or more advantageous. So we'll just solve for dy dx. dy over dx will equal, you subtract 2x, you divide by 2y, that will be negative x over y. And now we can plug in 20 and 15 and 20 and negative 15. So the slope for when you have 20 and 15 is going to be negative 20 over 15. So that means we'll get negative 4 over 3. If you reduce it and divide both by 5, and then on this side, the slope will be, you have negative 20 over negative 15, and that will give you positive 4 over 3. And that is the slope of these two lines. When x is 20, the slope is negative 4 over 3. When x is 20 and y is 15, that's this line. And when x is 20 and y is negative 15, that is our positive slope. And again, to get these two slopes, we plugged in x and y into our slope equation down here. So now we need to continue finding the equation of the tangent line. So we just need our y-intercepts now. So y equals mx plus b for both of these. So y is 15, our slope is negative 4/3, x is 20 plus b, so we'll get 15 equals negative 80 over 3 plus b. 15 is equal to 45 over 3, so we're doing 45 plus 80, which would be 125 over 3 equals b here. And then for our other line, we still have y equals mx plus b. So y this time is negative 15 equals positive 4/3. X is still 20 plus b. So 4 times 20 will be 80 over 3 again plus b. And this time we subtract it from both sides. So that's just going to give us negative 125 over 3 equals b here. And then our two equations, we have y equals, this slope is negative 4 over 3. X plus b, and then b is 125 over 3. And the equation on this side is y equals 4/3 x minus 125 over 3. Moving on to number 12. The position of a particle at time t is given by s. Find the velocity ds over dt. So we're looking for the derivative, and our variable that we're taking the derivative with respect to is t. So whenever we do derivatives of t, we don't need to put the ds over dt behind it. Actually, it will be dt over dt, which is 1. So that's why we don't write it anyway. But whenever we take the derivative of s, we will include the ds over dt afterwards. So we take the derivative, we'll have 3s squared ds dt minus, and here we're going to use a product rule, So this will be 5t ds over dt minus 5t. Nope, this will be 5s, sorry, because the derivative of t would just be dt over dt, which is gone. So then that is plus 8t cubed minus 7 equals 0. And now we're just trying to get our ds dt by itself. So we move the other term over to the right. So we'll have 3s squared ds dt minus 5t ds dt equals 5s minus 8t cubed plus 7, and then we divide after we factor out ds dt. So ds dt equals 5s minus 8t cubed plus 7 all over 3s squared minus 5t.